Um, the speaker today is Dan Huttenlocher. Dan is a computer vision researcher. He's on the faculty at the University of Cornell. Cornell University. I should know better than that. I was there for 6 years. As Dan's student, in fact. Dan has also been a researcher and a manager at Xerox PARC, and a software developer, engineering manager at financial software company, and actually usually more than one of those at once. So he's been a faculty member and a PARC researcher. And in fact, right now he's got a cross appointment at Cornell between the business school and the computer science faculty. Dan has won a number of awards for his teaching, and he's especially very good at getting undergraduates interested and involved in research. One of the undergraduates who he worked with this way, co-wrote papers with while the student was an undergraduate, was John Kleinberg, who some of you may have heard because it was his research later on while he was at IBM in the statistical structure of web links that led to people called Brin and Page to develop some of their early algorithms. So anyway, I've known Dan for getting on to 20 years now. I've actually worked with him at Cornell and at PARC and at the financial software company, and I'm very happy to introduce him at Google.
Thanks. So I just got done with a semester teaching in the business school, and I alternate. In the falls I teach in the business school, and in the springs I teach in computer science. And one thing about business school teaching is it's pretty interactive. So I'll expect you all to stop and ask me questions. And if not, I'll start cold calling on people in the audience. That's sort of a business school tradition, is to start asking questions. Dick's already looking at me saying, oh man, what questions is Huttenlocher going to come up with? But I trust in this audience people will keep me entertained with questions. But my goal is to get through as few slides as possible in my talk in general. That's sort of, it's more fun for me that way. So what I wanted to talk about today is some work we've been doing in my group on object category recognition. And this is, in the computer vision research community, this is sort of, seems to be the hot topic du jour. There are a lot of people working on this sort of problem lately. So if you look at kind of the history of object recognition in computer vision, it tended to be focused on very specific instances of objects, like not just recognizing bicycles, but recognizing my particular bicycle, and maybe not even the model of bicycle I have, but the ones with the scratches in the mud and in the exact places that they are on my bicycle. And in the last 5 years or so, there's been a bunch of work done on recognizing categories of objects in the computer vision community. And most of these are, and the ones that I'll talk about today, are what I would characterize as being visual categories. That is, they're categories of objects like a bicycle, where there's still quite a bit of variability in the appearance of these different bicycles. But they're still what I would say defined visually. If you start to think about a category like a chair, for example, which is defined more functionally, there are some chairs that look the same visually, but things like this strange egg that this person is squatting on, it's the functional role that defines it as a chair. And that's going to be beyond the kinds of algorithmic approaches that we're taking. And then, of course, you can get to these very abstract categories like vehicles, where it becomes much more semantic. And so I'll be talking about things where it's category recognition for these sort of visually defined categories. Now, within the task of object recognition in vision, there are two sort of complementary things that one can do. One is usually referred to as classification, which is determining whether an image has some particular object category in it or not. And then localization is telling where those things are in the image. And so if you're thinking about things like searching images, looking for photographs you have that happen to have cars in them or whatever, classification alone is enough. You don't really necessarily need to localize where those are in the image. On the other hand, if you're thinking of applications where you actually want to use the image data to interact with the world, or you want to do photo editing or things like that, then you care about actually being able to localize the object as well, and not just do detection or classification. And I'll be talking largely about localization kinds of problems today. in terms of imagery, everything that we've been doing in my group for years now has to do with recognition just from a single two-dimensional image. So we're not using anything like stereo vision for depth or temporal information that you would get from a video sequence. And so what I'll talk about is this localization problem for visual object categories in a single two-dimensional image. So when thinking about doing recognition from visual data, there are various cues that you can use for doing recognition. And generally, they tend to get divided into two broad categories in the recognition community under the names of appearance and geometry. So appearance is patterns. You can think of it like surface markings. If you, yep.
Sorry, just quickly back to your previous slide. Is classification a necessary precondition for localization or not?
It's an interesting question. So the question is classification a necessary precondition for localization? Most of the localization methods will sort of classify as part of the localization process, but the converse definitely isn't the case. There are classification methods that have no idea where the object is in the image. But the localization methods don't, for example, first classify and then try to localize. They don't say, somebody told me the object's in the image, now I have to tell where it is. They'll sort of do simultaneous classification and localization. So, but they do end up classifying in the process of localizing. And in fact, the problem of localizing, if someone told you the object is definitely in the image, is an easier problem than sort of doing simultaneous classification. You know, someone says, here's a picture of the car, tell me where it is, rather than here's a picture, what's in it, and then you know, if there's a car, where is it? So, but don't apologize for asking questions. That's good. Otherwise, I'm going to have to start asking questions. So in terms of recognition cues, appearance, you know, I sort of like to think of tiger fur as kind of a canonical example, right? It's sort of a pattern of intensities. And there's very little in terms of shape. I mean, a tiger can change its shape a lot, but from even just a little patch of fur, you recognize it. And that's sort of a canonical example of appearance. Whereas geometry is more both shape-based things and often spatial configurations of shapes or features. So a face is a pretty good canonical example, where you think of the eyes being located above the nose, which is located above the mouth, and so forth. And so that's sort of a configuration or an array of parts. And there tend to be some sort of canonical arrangement to those parts, except in the case of something like a Picasso painting, where the arrangement's somewhat distorted. So, and if you look in the vision community, these are problems people have been working on for about 45 years now, which started very much looking at geometry, and then there was a whole sort of time period looking at appearance, and the stuff I'll talk about and what's been going on recently in the community is trying to use those two cues together. So in using appearance in geometry, there's sort of, I think a good illustrative example is some work that's largely been going on in Pietro Perona's group at Caltech, which they call the constellation of parts models. And the idea is that they're going to detect certain kinds of features. And the easiest way to think of these features is just think of them as corners, but corners where you don't know the angle in the corner. That is, they're looking at things where there's affine invariant. So if you start looking at the shape of things, you can't actually preserve the corner. You just know that there's a corner. You don't know if it's 90 degrees or 45 degrees or what. And so they'll detect these little features. And then they have a Gaussian spatial model that says, given these detected features, what kind of configuration of feature locations correspond to the object. So it's a two-stage process where you first detect features, and these little dots here are various features that they've detected. And then you say, well, which features sort of fit some kind of Gaussian spatial model? And this is a picture from one of their papers that's supposed to indicate the Gaussian spatial model by these little cross-sections. So this is sort of like a level set of the location Gaussian. So this says, how much uncertainty is there in the location of this feature? And if you look at pretty much all the work that's been done in object recognition on these kind of generic category recognition problems, they all follow this general form where you're first detecting features, and then given the features, you're trying to match those to a spatial model. And in contrast, the work that we've been doing doesn't do any sort of separate feature detection. We're trying to do this as sort of one overall optimization problem. And here's a good illustration of the problem with feature detection. So here's actually a relatively decent corner detector in an incredibly simple scene, right? I mean, if you can't find the corners reliably in something like this, it's hard to imagine how you're going to do it in real-world scenes. And you can probably, even from the back of the room, see, for example, there's some corners here and here that are missing. There's some extra corners that have appeared in various places. These corners didn't get detected, and so forth. And the issue is one that sometimes in the computer vision community we call the aperture problem. But it's basically when you don't have enough context, a lot of these corners become very difficult to see. So the contrast here is actually very low. And part of the way you know that there's a corner here is that you see these edges converging on each other from further away. And if I zoom in and just look at a little local patch of this image, like over here, this corner, which is pretty evident here, is pretty much gone here. Because you don't, and I'm still giving you quite a bit of context here, right? If I zoomed in even further, you really wouldn't see the corner up there. And so when you're trying to make these decisions locally about detecting features using just the information in some small region, you're somehow throwing away a lot of the information that's important for doing detection. So the idea is that instead of trying to first detect features based on local information and then look at the configuration of features, since this feature detection process is noisy, can we somehow recast this as a problem where there's a single overall process going on? So does that, any questions so far? Uh-oh, we're getting dangerously close to me asking questions. It'll get more technical in a minute, and then hopefully people will have questions. So this idea is not a new idea. And in fact, if you look at a picture like that, you should immediately say, 1973, right? I mean, it's sort of this the cyber view of the world, version 1.0, back about 30 years ago. So there was a paper published back in the 70s by Fischler and Schlager on what they called pictorial structure models. And the idea was that these local sort of regions, like in a face, things like the eyes and the nose and the mouth and the hairline and the sides of the face, that this notion of these local parts is an important notion, and that those parts have some sort of pictorial or appearance characteristics to them, and then there's some structural relations between them. But what's different between this and the approach that I just described is that they didn't envision doing a process of detecting eyes and nose and mouth first. They envisioned doing one overall sort of process. And the way I like to think about it is, say you took this sort of abstract face model and you dropped it down on top of an image. And you start wiggling the pieces of this thing around and you say, where is this thing the happiest in the image? And what makes it happy is, well, if any of these local pictorial pieces are over some piece of the image that look a lot like, say, if the eye thing is over something that looks a lot like an eye, it's going to say, hey, I'm happy. And so it has a degree of happiness based on how much the image locally where you drop it down looks like an eye. And then these springs want to sort of pull the pieces into some overall spatial configuration. And if you're stretching the springs a lot, they get unhappy. So you can think of sort of plopping this sort of model down in an image and wiggling it around until it gets the happiest. And what's going to make it happier is when you move it around so that the eyes are on top of things that look eye-like in the image, and when you move it around so that these springs aren't stretched too much. Now, that's a very physical sort of description, and the problem is it's great to, you can get a nice sort of intuitive notion of what this sort of recognition of things like faces might be without doing feature detection. But that's not a very computational statement. Drop the thing down in the image and wiggle it around until it looks happy. So, and in fact, this sort of approach pretty much got buried in history because of the fact that nobody was able to really come up with reasonable computational approaches. So what we've been doing is investigating how to take this kind of a view of things where, so you can think of feature detection, right? as almost sort of an efficiency hack, right? If I process the image first and say, these are all the things that look like eyes, now I know where to start putting down this model. I'll put it down at the places that look like eyes. But if I somehow could take this sort of model and efficiently try possibilities without having to say where there are eyes or not, that would be less prone to error because I'd be able to use the context. Instead of trying to find one eye alone, I'd have the context of the other eyes and the nose and the other things that are connected to it by springs if I tried to solve this as one problem overall. So that's sort of the basic idea. And so what we've done over the last 4 or 5 years is develop a set of efficient algorithms that can solve matching for these pictorial structure models. And they're Gaussian spatial models. So they share with this work from Perona's lab that I mentioned a moment ago, the fact that there's some sort of Gaussian model of the relative positions of the parts of the object. And you can think of those as being spring-like models. The algorithms all make use of dynamic programming techniques to get a lot of efficiency. And I guess if I was going to stand on one of my soapboxes for a minute, I would say that as computer science educators, one of the places I feel like we sort of don't do a good job is teaching people enough about dynamic programming. That, divide and conquer is all over the place in a computer science curriculum, and yet dynamic programming to me is almost always the best tool to use for just about any problem. So, and I think it's just because it's harder to teach dynamic programming. And then we've also looked at learning these models from examples, and we actually get better recognition accuracy on some standard data sets that are used in the computer vision community than these techniques that rely on feature detection. And of course, that's what you would hope, since we're using the full context instead of trying to detect the features alone. So what I wanted to do is talk a little bit about some of these techniques, talk a little bit about how we learn these things from examples, and in general talk about the problem a little bit, touch on some issues about learning these sorts of models in images. So it's very important when you try to learn models for recognition that you don't presume too much supervision in the training process. So there's a paradigm that's coming to be used pretty widely in the computer vision community these days of a sort of weak supervision, where people give you class labels for the images. So they'll say this image contains, a car, or contains a truck, or contains a bicycle, but they don't say where it is. And that sort of labeling is a lot easier to get labeled data for, through a lot of these photo sharing and photo tagging sites and various things. I mean, you can get a fair amount of information about what images contain. But to actually get someone to painstakingly go and sort of say, here's the wheel on this car, and the next, forget it, you're not going to get data like that. So this weakly supervised process is something that's pretty important. So let me talk a little bit about the mathematical definition of the model and then kind of sketch how the algorithms work. So we're going to model an object here using a graphical model so we'll think about the parts as being nodes in a graph. We'll think about these springs that connect pairs of parts as being edges. And for each edge, we'll just have a Gaussian model of the relative spatial relationships between those two parts. So if the parts are just allowed to translate around in the image, then I just have a Gaussian over x and y, right, which over the delta x and delta y positions of the two parts. Simple two-dimensional Gaussian. And that collection of Gaussian pairwise models gives me an overall spatial prior on configurations of the parts. So if I sort of drop one of these models down on a completely blank image like this, where there's sort of no preference from the individual detectors, because nothing here looks like an eye or looks like hair or looks like mouth because it's on a white background, this thing will still reach sort of have a resting configuration where it's the happiest, which is the one that's the highest probability spatial configuration. And so that'll specify a separation of the parts from each other. And then the spatial configuration is taken over configurations. And by configurations, we just mean that there's some sort of set of parameters that describe the location of each individual part. And in a lot of the cases we'll look at, these will be translation, rotation, and scale in the image plane. But the simplest one to think about is where it's just translation in the image plane, because it's 2D and it's sort of just like the image itself. And then in these models, so this is one with 7 nodes and 9 edges. And of course, you could build a complete graph here where you had all the edges, all 21 possible edges between pairs. And then you would have one of these sort of full joint Gaussian models like have been used in some other techniques. So you can think about our models in some sense as encoding less information in that they're not trying to necessarily model all the spatial relationships. And that's going to be critical to being able to compute these things efficiently. The graph structure is going to matter. Yeah, so that's, yeah, so the question was, how do you decide how much to represent in terms of the shape? And basically the way we do that is the computational complexity is going to turn out to depend very directly on the graph structure. For example, if the graph structure were a tree, you can do this stuff very efficiently. There are certain other kinds of graph structures where it's pretty efficient. And so usually what we do is, so if you've picked a topology to the graph, then you can actually build the best, say, tree efficiently by finding the sets of parts that have the most dependable spatial relationship with respect to each other. In trying to decide sort of how much structure to put into the graph, there aren't any good automated techniques for that because it's sort of this model selection problem in machine learning, right, where if you're trying to sort of compare two different models that have different numbers of constraints in them, in some sense, the more constraints you put in, the more power the model has to represent things. It should be, until you get to overfitting, because you have so many zillions of parameters, it should do better and better. So what we tend to do is look for a sort of diminishing returns, where you add more structure and the performance starts to asymptote. But it's not theoretically as justified as the fixed model.
Can you take the complement of the graph and do something that the number can just become too large?
Yeah, so usually what we're going to do is the graph that we'll choose, its complement is still almost the complete graph. So the graphs that basically the graphs that we'll take have low tree width. And so that still leaves a lot of edges that are in the complement. So for doing image detection, basically there are sort of two. So we have this prior, which is the spatial model, the distribution over spatial configurations. And then we have a likelihood model. And this is sort of a big cheat. And it's a big cheat that everybody pretty much makes in the computer vision community except one person. And we actually, if I have time at the end, I'll talk about how we use some of the so there's a guy, Yali Amit, at University of Chicago, who's a statistician who has actually some nice techniques for dealing with this cheat. So here, the cheat is that we're going to model the likelihood as a product of likelihoods for the individual parts. So what we're saying is that the appearance of the parts is independent of one another. The spatial structure will encode all of the dependencies between parts. But, so for example, if we dropped two parts down on the same place in the image, they're clearly not independent of each other. They're explaining the same pixels. But there are even, subtler effects like, if the lighting changes, the parts will change color together. So we're not accounting for differences in appearance that would be modeled by some dependency between the parts. So we can do spatial dependence between the parts, but on the appearance, it's independent. And that's basically to get the problem to factor in a way where we have a computationally tractable solution. And pretty much everyone doing these multi-part kind of models in the computer vision community makes this cheat. Yali Amit has a nice way of dealing with this for the case of overlapping parts, which I may get a chance to touch on. So, but given this sort of model where you have the graphical model, you have the prior and the likelihood, then there are two things we can look at. We can look at the total evidence over all configurations. So in some sense, you can think about the configuration variable, which is telling you where all the parts are, as a nuisance variable. It's sort of, for each configuration, you've got some probability, which is, how good does the spring model or the prior say the thing is, and how good does the appearance model or the likelihood say things are. And then you just sort of want to integrate out over that variable. And that's the view that you take if you're trying to do detection without localization. right? You just sort of want to say, what's the total evidence in the image for this thing? Or the other thing you can do if you're interested in localization is you can take the quality of the best configuration. So these are map estimation kinds of problems. And then the maximizing configuration tells you where the parts are. Now, the problem is, in sort of viewing these two things that way, where you sort of say that the total evidence integrating out over this location variable will be my view if all I want to do is classify the image as having a bicycle or not, and I don't care about location. And when I care about location, I want to take the max. The problem is this is a sort of brittle view for localization, because the maximum probability thing may not be so great, because your models always have some inaccuracies in them. And so much of what we've done from sort of the statistical point of view over the last couple of years is to look at this view of things for solving that problem by basically using sampling techniques where we sample high probability configurations instead of taking the maximizer. And that I will, I think, get time to touch on. So I've been put up a few equations here. Let me try to explain more in pictures. So this slide, I want to stay on until people get, because this will sort of explain the approach. So, notation may or may not make sense, but if this doesn't make sense, do ask questions. So the first thing that we do is we have some image, and let's say we have a very, very simple model of a motorbike, which is just a front and a rear wheel model and some spring that says how far apart those things ought to be. And just for concreteness here, these front and rear wheel models, they're just going to be the probability of an edge at each location in some little template. So the contrast from the projector kind of washed this one out a bit, but you can probably or hopefully see a little bit of variation in these. So it's sort of brighter along here because that's the highest likelihood place for the edge of the wheel. It's pretty dim out there because the wheels sort of aren't that big, and this is sort of a little bit fat because there tend to be a bunch of edges from spokes and other sorts of things in there. And this front wheel model actually has a fork kind of going up there. There's a higher probability sort of region there from the fork of the bike. Now, obviously, this is a very impoverished model, just probability of an edge at each pixel. And if we were going to use edge-based models, we'd do something more intelligent, like at least use the orientation of the edges and so forth. But the things get too multidimensional to show on a screen. So we have those probability maps. And basically, I can take this and I can plop it down on the image. And at every position as I move it around, it's going to have some level of happiness in terms of, if I take this thing and I plop it right down on there, there's a whole bunch of edges right in a circle. This thing's going to be wildly happy. Yep, it's wildly happy. It's really bright right at that location in the image. Whereas if I plop it down at some location up here, it's going to be pretty unhappy, not so happy. So what each of these are quality maps that say, how well does this part explain the image locally when I place it down there? And not surprisingly, for this rear wheel, these two locations both look really, really good. But there are a lot of other locations actually here. There's a lot of stuff down here where there are edges that turn out to look pretty happy to that model. And there's sort of a placement here in the middle of the bike that looks pretty good. When you place the front wheel model down, it's a little more selective because it also wants to explain this fork piece that you can't quite see there, but believe me, it's there. And so it's much happier here. And it's still pretty happy here in the middle of the bike because there's some stuff up like that. But on the rear wheel, it's not very happy because there's not anything that looks very fork-like. So the idea is that instead of doing feature detection, right, what would a feature detector do? It would basically threshold this map and say, yep, here's a few places that could be rear wheels. And here's a couple places that could be front wheels. And you would just have this binary thresholding that you'd done to say, these are the locations where these things might be. And instead, what we want to do is not threshold those maps. We want to use the whole quality map. And we want to combine these things together directly in some fashion and only do thresholding at the end when we actually need to make a decision. So back a gazillion years ago when I was a graduate student, I used to have, this is typical MIT randomness. So yeah.
About that. Thresholding makes it sound like you're going to pick regions where it's above some probability of regions where it's not. You get these big bloody regions.
Yeah, absolutely. So in fact, a feature...
You want to do that anyway with this model?
Right, so what a feature detector would do, it's true, is it wouldn't just threshold, because you'd get these blobby regions, you'd do some non-maximum suppression-like thing to not only threshold, but also take the peaks of the stuff that were over the threshold.
If you were to sparsify it that way, you still get the probability measure. You don't just get a feature or not. You still get some measure.
Sure, absolutely. But this is a good place to roll up the sleeves and have a debate if you want, because so we're taking a very extreme view, but it's actually an extreme view that I'm gonna argue for. I mean, I'll have to be pretty bloody to get me to stop arguing for it, which is, or let me put it this way: no one's got me bloody enough yet. So it's true that you could. That you don't just want to threshold this because you get these big blobby regions. So non-maximum suppression or some other technique for picking not only stuff over threshold, but a local maximum. And then it's true that you don't have to just have that output that's the locations that satisfy that. You can actually have the strength at those locations. And so you can know that this is actually a better match than that is because it's a higher peak. But still fundamental to these things is that you're creating this sparse representation. And the question is why? That is, for example, in this case, it's a kind of drop-dead, stupid, trivial image, and it's pretty unambiguous that the things that match well locally are also going to match well globally. But if someone were standing over part of this wheel, for instance, then this wouldn't be real bright here. And so if I did my nice thresholding and non-maximum suppression and so forth, I wouldn't find anything there. And yet, when I consider these two things together, and I know that there's a spatial model tying them together, then the overall configuration, in fact, may still explain this thing very, very well. And so, but the only way I would argue that you can get that is to make no decisions at the beginning. Because as soon as you start trying to sort of build some sparse representation here, in the absence of the kind of context that you get from relating these parts to one another, then you're in danger of having made the wrong decision, and then it's hard to go back on it. So we want to keep sort of as much data as we had. Here's what I would argue is that the only reason you want to throw stuff out early is because you think it's too expensive to keep it around. Because otherwise, why not? And what I'm going to do is show you how it's not too expensive. That's sort of the sales pitch. But I should let you punch back now, because I give one long punch. So
I've been on both sides of this.
I know you have.
And I think there's a happy medium. It's okay for you to take an extreme view here. I want to see how it comes out. So go ahead.
Okay. So just what Dick was saying is he's been on both sides of this debate, and it's okay for me to take an extreme view, but by his tone of voice, he doesn't believe it's really going to work. Well, yeah, so I do presume I have these part models, and the question is, where did they come from? And basically, where they come from is an incredibly brute force process, where we start with a bunch of patches that we just sample at random out of a set of training images that we know are positive exemplars, so they must contain a motorcycle someplace, in this case of motorcycles. And then we look for individual patches that sort of seem to occur a lot. And then we try lots and lots of pairs and triples of these patches and look at how well they explain the training data. So it's just sort of, there's a very brute force process that builds kind of an initial model. And then we do an EM procedure to sort of improve on that initial model. But there is this sort of weekly supervised learning process where someone just said, here's a whole bunch of things that have motorbikes in them somewhere. And then we learn these models from that. But yes, we do need the part models to, so that's why in my talk where I said without the detection of features, I'm a firm believer in features. These local sort of descriptors are very important. But what I'm not a believer in is actually detecting the features individually. I think instead of detecting them, one should say, well, how happy is that part of the image to be characterized as being an instance of that feature? And then given these happiness maps, combine those together in some way and only make decisions at the end. And so what this is illustrating is sort of the first step in combining these maps together. So the problem is that if I want to take this map and combine them, I have some spatial uncertainty, right? It's not like I can just sort of take this map and sort of translate it over and plop it down on that other map and multiply the two together, because I have a spring there. It's not like I know exactly where these two parts are with respect to each other. I just know that they're probably here, and as I move them apart, I know how much less happy I am. And so what this is it's a transform of this map that accounts for that spatial uncertainty. And having done this transform, I now can actually take these two maps and multiply them together directly. And the key thing is that we can do this transform very efficiently. This transform turns out to be, so this is basically a lower envelope operation. Turns out to be a variant of a distance transform for those of you who are sort of image processing types who've looked at distance transforms. So we can do this thing really fast. And of course, I made the critical mistake of not taking out of my bag. So this is the one thing about having questions along the way, is I never know how long I've been talking for, so I have to.
Why is the low pass filter on?
So because what this is doing, if you think about what's going on with a spring model, what's going on with a spring model is that as I stretch these things apart, it's getting, say, in fact, a quadratic is a pretty good spring model, right? As I'm pulling stuff apart, it's getting quadratically less and less happy. So I don't want to just sort of blur this thing out in some arbitrary way. I want to actually encode the real underlying Gaussian spatial model or spring cost model.
But that wouldn't be a convolution with a Gaussian?
It can, in some cases, it's a convolution with a Gaussian, but in this case, where what I'm trying to do is actually this minimization, it isn't actually convolution with a Gaussian. It's basically, instead of a normal convolution, which is sum product, it's over the min-sum semi-ring instead of the sum product. So basically, you take the sum in a convolution and replace it with a min. You take the product and replace it with a sum. And that's what that operation actually is. It's sometimes called the min convolution because it looks like convolution except with a min in it.
I'm not an expert on random fields, but how different is this from random field model? It seems like it's a dual of the.
That was such a I swear I didn't plant that question. This is a Markov random field model. And so this is it's a probabilistic model where so it's a graphical model where there are undirected edges. So it's looking at correlations between things rather than causality, which is the sort of traditional directed graphical models. And those are Markov random fields. So all a Markov random field is a collection of random variables where you have correlational connections between certain pairs of the random variables rather than causal connections. And the nice thing about sort of viewing these things, so MRFs are just amazingly powerful. One sort of footnote, if people don't know about Markov random fields, and if you spend any of your life looking at models where you have several random variables where there are correlations between certain subsets of the random variables, you should go look at Markov random fields. They're really a very nice formalism. Because the tendency, if you don't know about MRFs, is just to throw this into one gigantic model, right, where you look at all possible correlations between things, like build something like a complete Gaussian model. And the MRFs where you just look at certain subsets of the graph, of the complete graph, can be very useful. And in these graphs, reachability in the graph basically corresponds to conditional dependency, right? So if I take this node and I take it out, then these nodes are all conditionally independent from one another.
So are you saying that if you sample your Markov random field, you end up generating faces that will probably...
Yeah, actually, so if we just take, so the spatial model is an MRF, is a Markov random field. And if we just sample from that, we get really good human body configurations, for example, in a human body model, or really good face configurations in a face model. And that's sort of, these are generative models, so they're a way of sort of testing how good your spatial model is to sample from it. And if you start getting things that don't look like faces, for example, in your face model, then you understand where there are weaknesses in the underlying model. So the human body, I think, is the easiest illustration of this. So these are a kinematic. So the great thing about a human body is a tree is a natural model, because the kinematic structure is a tree structure. The skeleton forms a tree. So in this sort of MRF thing, we have the parts are these sort of simple body parts, and those are the nodes in the graph. The joints between connected pairs of body parts are the edges. And we're going to look at the 2D image of a joint. And so the spatial configuration that we'll have looking at a 2D image is, so say this is a torso and an upper leg attached to it. We'll look at the relative position, orientation, and a scale of these two things. So we get foreshortening of the parts. So the nice thing about trees, and this is a factorization that's been known for a long time, is that in a tree, this spatial prior factors very cleanly. It factors into a product over the edges, or the connections between the pairs of parts, and a product over the individual components. And in fact, because in our spatial models, we're only modeling relative location and not absolute location, this denominator disappears. Because we're not saying that it's more likely that the leg be here in the image than here in the image. What we're saying is it's more likely that the leg be here with respect to the torso. So it's only the pairwise components that matter. And in this sort of a tree structure, you can sort of directly apply the traditional Viterbi algorithm, where instead of recursing on the length of a chain like you do in Viterbi, you recurse on the depth of the tree. And that's, again, something that's been known for a long time. The problem is, in this sort of world of human body models, it's not all that practical to apply Viterbi here, because the great thing about Viterbi, it's linear in the number of elements. But that's just the number of nodes in the tree here. And it's quadratic in the product of the state spaces of elements. It's quadratic in the state space size of the two of elements, right? So there's a sort of trellis in the Viterbi algorithm. You get something quadratic in the state set size. And the problem is that our state set here is locations per part. These are position, orientation, and scale. So there's maybe 5 or 10 million of them per part. And 5 or 10 million squared is just not a very happy number when you're trying to do things at, say, video rates. So this is a place where there are a bunch of fast methods that you can use. Because we're only concerned about relative locations, instead of really modeling the cross product of locations of pairs of parts, all you really care about is that's just proportional to some function of the difference between them. And so, as Dan was suggesting, you can use convolution or FFT-like operations. In fact, because these things are Gaussians, you can do something better, which is binomial filtering, which doesn't have the log and doesn't have some of FFT's annoying sort of boundary condition things. For finding the best match or the map estimate, there are these new methods for doing linear time lower envelope calculations, or min convolutions, that we've developed over the last few years. And that's the sort of picture I showed as the example, which is one of these min convolution or lower envelope calculations. So in doing the best match, and I wasn't going to talk about the algorithmic details any more than that, because there are papers on that stuff. So if someone's interested, I can point you at those. So in doing the best match, right, we're considering all possible spatial configurations in an implicit sense, right? But most of them are being eliminated because it's a dynamic programming solution, right? It's like Viterbi is a dynamic programming algorithm. There's an exponentially large space, but most things don't have to be considered. But the problem with finding the best match, which is what Viterbi is doing for us, is that these models are very impoverished. And I think, in general, any models that you're going to have for interpreting image data or many other kinds of noisy data, the model's never going to be right. And so as soon as you have model error, finding the best match is a very dangerous thing to do. What you really want to do is find some sort of population of fairly good matches and try to be able to consider those in a reasonable way. So here's a case where the min-cost match is sort of clearly a little strange. This is a very simple appearance model where it's just a binary silhouette, just as an example. And it's perfectly happy to place this arm down here instead of placing it up overhead, because this stuff looks as arm-like as that stuff up there does. And this model is just, the model's just trying to explain the image data underneath it. It's not trying to explain the whole image, right? Because there might be other stuff in the background here so there's sort of no way in this kind of model to really get it to prefer this sort of thing, except maybe in our spatial prior to have lots of pictures of people standing like this, right? The reason it preferred this is because this is closer to a sort of default configuration. You know, we took a bunch of pictures of people to build that spatial model that, so this spatial model here was actually built from a bunch of training images of just people sort of standing in different kind of standing poses. And that was sort of the average image. And so when you apply that sort of model to something like this, having this arm down just looks a lot better than having it up. So the answer in this kind of formalism to that kind of problem is to, that's interesting. So there's some disappearing stuff. Ah, yes. PowerPoint. So that the way we deal with this problem is actually to sample, is to look at this sort of total evidence view where you're viewing configuration as a nuisance parameter to integrate out. So we actually, from the statistical or Markov random field model sense, we compute the actual posterior distribution. Because of the fact that it's factored into this simple product, we can actually compute the thing. And then we can sample from the posterior distribution. So this first is just this same example, and these are a bunch of samples that are high posterior probability. Now, if, in fact, I just had no input image, then it would be back to your question before about if we just sort of sampled from the prior, would these things look human-like? And then you'd sort of get people standing like this. But these are samples from the posterior where we are taking this appearance information into account. And here's the thing that was the map estimate. That's high probability it gets sampled. But here are some other high probability samples. And this one actually looks a whole lot better. So one of the things that we've been doing quite a bit of in these models is sampling. And in fact, there's some work that came out of Dave Forsyth, who's at University of Illinois now, and Andrew Zisserman at Oxford, together with a student of theirs, Deva Ramanan, where they used our algorithmic techniques for doing the Markov random field modeling and sampling from the probability distribution. And they put a lot more effort into developing good appearance models for the parts. Right? This is a pretty cruddy appearance model. It's just a binary silhouette. And they have some really impressive, if you look at Deva Ramanan's website, he has like this 9-minute video of Michelle Kwan in a championship, in her championship skating appearance. And it tracks all the body parts through the whole 9-minute video. It's really quite amazing. And so these algorithms are now being used by stuff I didn't do, so I can say that it's the best, but being used by techniques that really do a good job of pretty low resolution video, stuff from sporting events where you don't have great resolution in the video. So I don't know if Dick, if this starts to answer the does this stuff work or not, but.
Can you say again how you're able to get away from the priors, having the priors? I just kind of missed that.
So it's not that we get it's not that we get away from having the prior. So the prior is part of our model, and it's basically intuitively this is sort of the idea. It's that we want to use the prior to bias the set of solutions, right? That's what priors are supposed to do. And the problem is when you do map estimation, right? Just sort of compute the best match. You're picking one solution that maximizes the posterior distribution, right? You're taking the prior into account and forming a posterior, and you're picking a maximizer. And instead, what we do is we sample. So you can think of that whole posterior distribution For every configuration, it says how happy, what's the posterior probability. And we just sample a bunch of high posterior probability configurations.
So it could be like n best, where n's a large number, and you average over that.
Yep, it could be n best, and you do some sort of smart averaging. It can be that you have some other information that allows you to select among those things with a hypothesize and test kind of paradigm. In a bunch of what we've been doing lately, we basically do a sort of simple hypothesizing. We use this as hypothesizer and do some very simple testing at the end. But the key thing, in my mind, that actually makes this stuff work is that it's not based, in these kinds of videos, if you tried to actually, detect where her legs and stuff were on every frame and then impose the spatial model after the fact, the results wouldn't be very good.
So it's more robust.
That's right. It's basically what you get is more robustness by making decisions at the end. Yeah.
I had two questions. So the first question is, how do you get your prior model? Is it from video samples?
So the prior model comes from some, this is the perennial machine learning problem. Somebody gives me a set of positive exemplars and I learn a model from it. And if it's a good set for my test cases, then I get a pretty good model. And
because I was thinking, there's tons of, especially for human motion, there's tons of 3D capture examples that are available off the web.
right. So
How do you use those for?
right. So one thing that we have done we've looked quite a bit at human motion, and for the human motion data, we have developed some models with mocap. One of the things about human motion is that you really want to augment these tree models a little bit. So, I mean, the thing about human motion is that you have to maintain balance. And in maintaining balance, there's essentially, what balance is essentially from a geometric point of view is some sort of symmetry, right, around the center of gravity. So the tree model only accounts for the kinematic constraints. And so what we actually end up doing for the human body model is to, the nice thing about graphical models is you can have nodes in the graph that don't correspond to actual parts in the real world. So we have latent variable in this model that essentially is measuring the degree to which the model is balanced. And that actually helps a lot for these kinds of things where balance is really critical. But again, you learn that balance parameter from a bunch of training data. So probably I should more or less wrap up. So let me just sort of, and then I can take some questions offline. So what we've been working on is doing detection and localization without doing the separate detection of individual features. And although I didn't actually get to it in the talk, but there are papers on this stuff. But for a bunch of common data sets that people are using in the vision community these days, we actually get more accurate detection of these kinds of generic models like people and bicycles and so forth than the best techniques that do localization and use feature detection as a separate step. And then the spatial structure stuff I didn't actually get to talk about, so I'll just briefly mention here, as I started to before, I think in response to Craig's question. So the tree model is a place where you can naturally apply the Viterbi algorithm, but it doesn't have a whole lot of constraint in it. And there's another sort of family of models that we've been working with where you can apply a sort of variant of Viterbi. And in this family of models, so a star graph is just a depth one tree, right? You've got the root, and then you've got all the nodes that are one away from the root. And there's a way to generalize a star graph, which is instead of having one node at the root, you can have two nodes at the root that are connected to all of the nodes. So now you no longer have a tree. You have something where you have a pair of nodes connected to every node. Or you could have a triple of nodes that are connected to every node. And of course, as you increase the size of that set, eventually you get up to the complete graph. And that family, which are called K-fans, because they're sort of they're fans or star graphs where you're building bigger and bigger cliques in the middle. That family turns out to be a family where we can sort of naturally look at these kinds of questions about how much spatial constraint you want to put in the model. So just in terms of where things are going on these kinds of problems, both in what we're doing in our group and what's going on in the computer vision community more generally, the vision community really sort of took some data sets and beat them to death, past death. So one direction in which things are going in the vision community is things with larger and larger numbers of object categories in them. But the direction that we've been taking in our work is actually not so much going to bigger and bigger sets of categories, sort of staying with tens of categories, but actually looking at much more complicated scenes. So rather than pictures where there's a motorbike filling 80% of the picture, dealing with scenes where there are lots of different objects in them, and much more view variation than in the kind of example image from the motorbike. And once you start looking at those more complex images, there's a lot of opportunity to use contextual information at the scene level, right? So everything I've been talking about this pictorial structures approach to recognition is using context. Instead of detecting the features individually, you use the contextual information at the object level and use that to help you. You can also use contextual information at the scene level. If you've found two cars that are sort of lined up with each other, then other car-like things that are lined up with that are much, much, much more likely to be a car, because cars tend to drive on roadways. Same thing with people. So as you start looking at more complicated scenes, you can again take this whole thing one level higher up. Instead of detecting the cars, you can have a car model, and you can say how car-like is each part of the image. And then you can use constraints at the scene level to say there's a bunch of car-like stuff in some organization. You have a prior model on the scene, and that makes it more likely that you'll detect the individual cars. So, and in general in the recognition community right now, there's a lot more work going on starting to use scene context and not just doing detection of individual objects. So that's pretty much what I had to say. Are there other, it's been good. We've gotten questions along the way, but Dick must have a question.
Yes, I don't understand. You said it's faster. I don't understand why or how. And normally when I think about kind of perceptual processes and maybe the way human brains do it, I think about there being some kind of a funneling process where you kind of narrow down your options on the way up and reinforce that with the top-down stuff. But you're doing minimum narrowing from the bottom-up stuff. Why does that come out faster?
So that's a good question. So the question is, how could this possibly be faster, both biologically and from an algorithmic perspective? You want to sort of narrow things down and have sort of top-down and bottom-up kinds of constraints.
Yeah, you don't want to make too many decisions too early, but some can help.
So here's how I would think about what we're doing here. Basically, what we're doing is we're using the top-down information in constructing essentially richer and richer versions of these maps. So when I go back to this sort of picture, and I sort of construct this compound map that is the appearance for the rear wheel, but taking the position information for the front wheel into account. This map has used top-down information in constructing it. It used the bottom-up information from here, and it used the top-down information from the spatial model to build that. So basically, what we're doing is we're bringing top-down and bottom-up information together in this process. And the fact that, and essentially, the detection of individual features, I would argue, in fact, is the wrong way of, or a bad way of winnowing things down, because it tends to end you up with a combinatorial kind of problem. And that's why these things end up taking longer, I think, if you do feature detection. Because if you detect the individual features, but you know you're making mistakes, so you know you're going to have extra features that you can't account for, and you know you're going to have missing features that you're going to have to sort of go back and try to look for. You now have this nasty combinatorial problem because you're essentially doing subset matching. Because it's a subset of the image features because some of them might be extra, and it's a subset of the model features because some of them might be missing. And those kind of combinatorial subset matching problems are just unpleasant. Whereas if you stay in this sort of representation, this kind of dense representation, where you are definitely, this representation is much more winnowed down than that one, because it took the spatial constraint into account. But we don't winnow it down in the sense of the data structures. We winnow it down in the sense of the information that's present in the same data structure. So I would argue what we're doing actually is, so I think you're right about the way these things happen, and it's just that, too many of us have too much computer science training where we think, combinatorial algorithm, good thing. And the problem is, when it turns into a subset matching problem, it's not a good thing. You're better off dealing with lots of pixels and lots of subsets. That's a very good way of, that's a better way of summarizing it than, so. Anything else? Great.